Welcome. Welcome to a new event from LD Didactic. Today we have a new webinar in the field of power engineering. My name is Helmut Höfgen. I'm Area Sales Manager at LD Didactic, and I'd like to introduce our colleague, Dr. Simon Kozea. Simon is our expert in the field of power engineering, and he knows best the new products we want to introduce today, the controllable loads. For the beginning, we'd like to switch over to a PowerPoint.
Thank you, Helmut, for the kind introduction.
You're welcome.
As Helmut stressed out already, I want to show you two topics today. And the first one is our new product, controllable loads. This represents resistive, capacitive, and inductive consumers. And the three-phase loads can be used universally in the fields of power engineering or control engineering. But of course, you can also demonstrate the basic of electrical engineering with them. One of the main features of the loads I want to stress out is that they are remotely controllable. This allows us to feature remote controlled complex load scenarios and enable experiments on smart grids. As an example, we will later run a standard load curve from a German household in the following. Now I will show you the properties and specification of the loads, and we'll then go to the live experiments on grid analyzers with the Power Analyser CASSY Plus. We will show how a neutral point shift comes together, and I will show you how harmonics are measured with our measurement tool CASSY Lab 2. In all our cases, measuring and controlling the loads will be done with the Power Analyser CASSY Plus. We will finish our talk with a short Q&A. Let me start with the controllable loads. Here on the right-hand side, the front plate of the load is depicted. We have three types of load: ohmic, capacitive, and inductive. The R and the C loads come in two power levels, which are tailored to our electrical machines, and they have a maximum power consumption of 300 watts or VRR, or 1 kilowatt or VRR respectively. The inductive loads has a maximum power consumption of 470 VRR. They have 16 defined load steps, so that the entire power range can be well represented. With the combination of several units, you can, of course, merge them together. More stages or even finer steps are available, and you can even choose to have a higher power consumption. The active level and the status of the load is indicated by LED bars on the front panel. The loads have three operation modes. The manual operation mode, where you control the load directly on the front panel. The remote control load, where you can, for example, use our Power Analyser CASSY Plus to control the load via our interactive instruction sheets or via our measurements tools via Wi-Fi. Or we have the triggered load, the triggered mode, which allows us to trigger an unbalanced load configuration. Before I present you the loads in a live experiment, I want to shortly explain the elements on the front panel. We have the main switch on the top right hand to switch the load on and off. You can connect the phases here on the left hand side, and they are short circuited to the right hand side, so you can expand your setup or experiment with further loads or further equipment. You can control the load step with buttons on the front, and can turn on the load with the buttons here on the left hand side. The control input to remotely control the load is located here at the bottom left. Okay, now I want to show you how you can manually control the load directly on the front panel. Helmut will turn the camera on. Okay, thank you, Helmut. Here the load is in our experimental stand. You can see we can use it in a stand, but it also has a tabletop unit to place it directly on a table at a pupil's desk or at the teacher's desk. In the manual mode, you can control the load with the buttons on the front, and you can set, for example, an unbalanced load configuration. I've chosen step 2, step 3, and step 7 for each individual phase, and will enable the load with the press of the set button. Here in this mode, we are allowed to use unbalanced configurations, but you have to think about it because some configurations can stress your other equipment. Load can be turned off with the button press off. If you don't want to use unbalanced configuration, you can couple each phase with another. You do this by pressing up and down simultaneously, and then press the up button on the phase you want to couple, and now are allowed to control all phases at the same time. You can turn them on and can turn them off again. Okay. The next mode is the remote control operation. For this, we use our Power Analyser CASSY Plus and use one of the outputs of the Power Analyser CASSY Plus, output U here, and connect them to the control input. I will enable the output and select the load mode at the output. Now I can use the interface of the Power Analyser CASSY Plus to directly select the desired load step. For example, load step 10, which switches on the load with a resistance of 233 on every phase. You can switch to the next step or turn off the load at the interface. The main benefit of this remote control mode is, of course, that we are able to connect to the Power Analyser CASSY Plus with our lab docs or with our measurement software CASSY Lab 2, and then control the load via these two instruments. So students can directly control within the instruction sheets the load, and are able to vary the power consumption in their setup. The third mode is the triggered mode, and I will activate the triggered mode. And with this triggered mode, I forgot to tell you that in this remotely controlled mode, you're only allowed to use balanced load level because we don't want you to use unbalanced load levels in a remote way. With the triggered mode, you are again allowed to do this. I choose the triggered mode on the interface of the Power Analyzer. I pre-select some load configuration, maybe balanced or unbalanced. And now I can go to my lab doc or at the interface and turn on the load to a predefined time. Now I want to turn it on directly in this unbalanced load configuration. Okay. These remote control features allows us to run complex load scenarios. And for this, I want to show you some standard load curve we want to simulate now. The load curve is the load curve of a standard. Helmut, can you please switch to the, thank you. The load curve you see here, on the x-axis you have a time scale of 48 seconds, which corresponds to 48 hours in real time, so 2 days are plotted here. And on the y-axis you see the power consumption taken by one German household on winter days. The first 24 hours are a normal weekday, where the people start to boil coffee in the morning and cook dinner in the evening, and the next day is a holiday, where the power consumption is a little bit higher and everybody's at home and cooks more. With this, our loads are able to follow this curve, and for this I want to launch another CASSY Lab measurement file. I will connect to our Power Analyser CASSY to control it. You can close this now. And when I start the measurement, you will see the predefined load curve in pink again, and the consumption, the power consumption measured by the Power Analyser CASSY Plus on each phase in blue. Started. I will stop it again, and of course I have forgotten to turn on the power supply. So I will just start the measurement again. So now you can see pink curve is the predefined load curve of our German standard result, and the blue is the power consumption drawn by our load. As you can see, it is switched in steps because we have 16 steps to cover the whole power range, but we can closely follow the predefined power consumption curve. In the picture in the feed, you can also see how the load is controlled remotely and the power levels go up and down. Okay, at the end of the second day, the power consumption starts to fall, and when the measurements end, the loads will be automatically turned off. Now, these scenarios allows us for smart grid experiments. For example, you could use this load curve to put some load on a generator in combination with the grid or in combination with a photovoltaic inverter, and see how they operate together. You can are now able to shift power from the generator to the inverter depending on the load conditions you have seen here. I will close this and come back to my talk. Just want to sum up what I've told you about the loads and point out some more advantages. We have 3 operation modes. We have the easy operation in a standalone mode directly on the device. There is no additional controller needed, and you can replace old loads in your existing experiments without further hassle. You can also remotely control the loads, for example, with our Power Analyser CASSY Plus via the interface directly on the CASSY device, via LabDocs, via CASSY Lab, and because our Power Analyzer supports LabVIEW, you're also able to control the load and measurements with LabVIEW VIs. We are able to trigger the loads to enable measurement synchronous measurements, even of asymmetrical loads or unbalanced loads, and you have indication of the active step on the front panel of the loads. The loads allow for continuous operation. We have load-controlled fans in the housing, and we have also additional temperature monitoring and burn-off-proof resistors. So if there's an overload, it will switch automatically off and will not damage the device. This is not the internal phase detection. It's not really interesting for the resistive load, but the capacitive and the inductive load are only switched on at the correct time when current or voltage, depending on the load type, are at 0. I've told you earlier that the housing for the load is able to be hung in an experimental frame and also placed on the table, as you can see here on the picture in the bottom left. Okay, now we are coming to our next experiment, and here I want to show you how the neutral points or start points shift with balanced and unbalanced load depending on the connection of the neutral point to the grid. The experimental layout is printed here on the slide. In the left we have the power supply connected to our Power Analyser CASSY Plus, which measures current and voltage on each line individually. And this is connected to our load on the right-hand side. As I've told you earlier, the control input in channel, control output in channel U is connected to the load, so we can remotely control this with our instruction sheet. And now I will load the instruction sheet from our digital solution Laylab, where all the sheets are saved for you. I will start up the Scholar version because I don't want you to see the solution for the questions in beforehand. Okay. In every sheet we have a short introduction, and of course this experiment needs some special instruction because unbalanced loads in 3-phase power system can cause voltage surges on one of the phase or even 2 of the phases, which can lead to higher voltages or higher currents than expected and desired. So here, when you put an unbalanced load on a 3-phase system, you have to know exactly what you have to do. We set up the experiments as I have shown you on the slide. The pupils have here a wiring diagram, so they can do this on their own. And the teacher would have the picture I showed you earlier to control the students. We connect the laptop to the CASSY Plus Power Analyzer. I've done this already. We are connected via Wi-Fi. And we will now test the setup by just increasing the load level on the load with the push buttons. And you can see in the picture-in-picture that the load level is increasing, and the power analyzer measures here an even current on each phase. So the setup is built correctly. And now I can turn off the loads again. Then we can start with the exponential procedure. At first, we will want to measure a balanced load with and without the neutral connection N. We will switch to the correct measurement series. And when the series is loaded, you can see a vector scope of each phase. Line 1 corresponds to UA, 2 corresponds to UB, and 3 to UC, as you know it. We have a phase angle of 120 degrees between each of the phase line voltages. And as expected, we have a voltage of about 230 amperes. Already with a slight imbalance coming from our grid here. Now I can increase the load level, for example, to step 6. And what we see here on the vector scope is that the current is increasing, of course, because it's a balanced load in an even manner. And the phase angle of each phase stays the same at 120 degrees, and the current is still in phase with the voltage on each corresponding phase. The lab docs asks us to do 3 measurements. We want to record current and voltage at 3 load levels, at load level 1, at load level 5, and at load level 10. So for now, we have done all the measurements with the neutral connection connected to the grid. And now we disconnect the connection. I will just plug it out here and put it into the voltage input of our Power Analyzer Plus, where we then can measure the voltage on the neutral point. As can be seen here in the next multimeter, the voltage is now about 1.3, which comes from the slight imbalance already present in the grid, and we can do nothing against this. Even if I increase it to higher load levels, you can see the voltage stays nearly the same. Current is now at 1.4 amps per phase. The lab docs asked us to do 3 measurements again at 1, 5, and load level 10. Okay, after doing all the measurements, we will turn off the load. And now comes the interesting part. Repeat this experiment with an unbalanced load. I will switch to the next measurement series. Okay, we can see again 3 phases at the moment still balanced because we have the load turned off. And now I will manually set on the loads the phases to load level 13 on phase 1 and load level 7 on phase 2 and 3. Okay, so I will dial in load level 13 at phase 1, and I will couple phase 3 and 2 and dial in load level 7 at phase 2 and 3 and come back now to my lab doc, where I can trigger the load using the following button. And please pay attention to the vector scope during this. Okay, what have we seen here? Now, the phase angle between phase 2 and 3 are 130 degrees corresponding to the first phase. The voltages have increased to 260 volts, and the voltage of phase 1 has decreased to 177 volts. Additionally, we have potential at the neutral point of about 50 volts. Let us save this measurement and then reconnect the conductor between the neutral points. For this, I will go to the Power Analyser CASSY, unplug it, and just put it into the current measuring input here. Have you seen what has happened to the vectorscope? I will just unplug it again. Here we have an unbalanced load without neutral connections. And here we have the balanced load with neutral connection. Let us save this measurement and then turn the load off directly in the instruction sheet. Okay, the experimental part is over. And now we can look at our measurement results, which are recorded here nicely in these tables. For the first table is a balanced load with and without neutral point connections. All the voltages are the same. And the current and voltage here at the neutral point is low as expected for balanced loads. For the unbalanced loads without neutral connection, we see that we have an uneven values in the voltage. We have even a 50 volt neutral point shift, and for when we connect the neutral point, we have a high current on the neutral conductor. Your students are now tasked to describe the observations, but for this I will go to the teacher's manual, because then you can see all the solutions already. I can go through their observations, and then if they want to, they could calculate the neutral point shift on their own using this template here. We have the resistors, which we have the resistor values, which we have selected by selecting load level 13 and load level 7, and can then use complex AC calculations to calculate the neutral point shift with a value of 50 volts, and from this calculate the resulting line voltages. Okay, so far for the experiment on the neutral point shift. Let me close this and come back to my presentation. On the next experiment, I want to show you how we can measure harmonics up to the 5th harmonic with CASSY Lab 2. The layout of the experiment has not changed much. We have the same setup, the power supply on the left, the Power Analyser CASSY in the center, and the load connected to the right-hand side. And to the first phase of the load, we have connected 3 LED bulbs, which we can switch on and off with a small switch. I will now launch my CASSY software, where I can show you the measurement of the harmonics. I will have to, of course, sorry, I have to close the LabVIEW files, the LabDoc files, and then connect to my Power Analyser CASSY again. Okay. What we now see here is the measurement of voltage and current in the interval of 100 milliseconds, so 5 periods of our AC grid of line 1. And when I start the measurement, you can see, okay, this is the live measurement. We have activated load level 1 at the load, so a small current is flowing through line 1. When we now look at the fast Fourier transformation of the signal, we see that at the 0th harmonic, at the ground order, we have a peak, and at every other order, so at the 3rd, 5th, 7th, we have only very small peaks barely visible, so no harmonics at all present in our system. When I now turn on the LED bulbs, I will go over to the experimental stand. Sorry, and switch on the LEDs. They're connected to phase 1, as you can see here. Then you see we have many harmonics at every order up to the 5th order, especially at the lower orders as expected at 3, 5, and 7, but also every other order is affected. With the Power Analyser Plus, we would be able to measure the harmonics even higher, up to the 100th order, but this is not really relevant in power engineering. Let us check where these harmonics come from, and of course, as expected, looking at the IV graphs, we see that the bulbs cause a huge distortion in the current because of the solid state power supply modules. Okay, I will turn the LEDs off again. And you can see everything is back to normal. Okay, I will stop the measurement and go back to my presentation. So, these were the 2 experiments I wanted to show you. Firstly, I've shown you how our new loads look like and what the features of the loads are, and then have shown you how we can show students what a neutral point or start point shift is, and how voltages rise and fall on each phase with an unbalanced load when the neutral point is not connected. And I've shown you how you can measure harmonics with our CASSY Lab 2 software. Very simple in combination with the Power Analyser CASSY Plus.
So we come to the end of our webinar. Simon, thank you very much again for this nice demonstration during the experiment and products demonstration. Thank you very much for your attention to our webinar, and we are looking forward to welcome you back here in our webinar soon. Bye-bye.
See you soon.